Let's talk about orientation. So orientation for Stokes's theorem is kind of important to remember. When we write down our curve that we're going to be doing a line integral over, and when we write down our surface that we write down a two-dimensional integral over, both of those have orientations. The curve has a direction that it's traveling, and the surface has a normal vector that tells us what's up and what's down. And for Stokes's theorem to be true, we need those to match in a particular way. When we talked about Green's theorem, we had this rule that if we had a double integral over a region being the same as the single integral around the boundary, we had to line those up properly. The object had to be moving counterclockwise around the region, or if we're kind of walking around the outside boundary, we need to keep the region on our left, was the more precise rule. With curves and surfaces in 3D, the shapes can be much more complicated. They can be kind of upside down, go around, all kinds of stuff. And so as a result, it is important to be a little bit more careful about what exactly we mean when we relate what's going on with a surface and what's going on with a curve that goes around its boundary. So that can be tricky to make sure we match those up properly. The curve has a direction, and the surface has a normal that tells us what is up. So here is how we match those things. What we do is we imagine ourselves walking around the outside boundary along the direction of the curve. And the surface has a normal that tells us what direction is up. We point our head in the same direction as the normal vector. And then as we're walking in this direction forwards with our head pointed towards the normal, the region that we're integrating over, the surface, should stay on our left-hand side, the same as with Green's theorem. So here's an example. There are 4 examples of how we can have a curve going around the boundary of a surface, and the surface has a normal and the curve has a direction. And some of these orientations match and some of them don't. Here, for example, in the upper left, if we're walking around this curve with our head pointed towards the normal vector, the region is going to be on our left, and that's okay. Whereas if we're walking around the opposite direction with our head pointed towards the normal, the region is going to be on our right, and it's going to be wrong. Here, in the bottom left, we have to imagine ourselves instead walking around this curve in this direction, but now with our head upside down, and try and figure out whether this is oriented properly or improperly. This one, it turns out, is improper, whereas this one is proper. Now, unfortunately, this gets a little confusing and people freak out over this quite a bit. So here's another version that some people find a little bit easier, and I apologize for this drawing of a hand. It is the best I can do under the circumstances on this screen. What you try and do in this version is you hold out your right hand the same way as if you were making a coordinate axis. You point your index finger in the direction of the curve, and you point your thumb in the direction of the normal vector, and you try and push your middle finger into the surface, as if you imagine your hand as being kind of like a can opener that's running around the outside edge of your surface. And if you can do that with your right hand, then it's properly oriented. And if it's with your left hand, then it's improperly oriented. So that's another way to remember this matching orientation. But having said all this, if you get the orientations not matched properly, you will get an extra negative sign out at the end. And it's not that big a deal from the point of view of calculating things on an exam, but it is kind of a big deal if you get the opposite value when you're actually doing this in a real world problem.